Have you ever looked at a massive dataset, perhaps with hundreds or even thousands of features, and wished you could just see the hidden patterns and relationships within it? It can feel like trying to understand an intricate tapestry by only looking at a single thread. This is a common challenge in data analysis, and thankfully, we have powerful tools to help us gain clarity, one of which is called t-distributed stochastic neighbor embedding. Perplexity is a fundamental parameter in t-distributed stochastic neighbor embedding, or t-SNE, that directly influences how the algorithm balances its focus between preserving local and global data structures in the lower dimensional map. Essentially, it controls how t-SNE considers its neighbors, making a crucial difference in the visual outcome of your data exploration. So, why is perplexity such a big deal? At its core, perplexity can be thought of as an effective number of nearest neighbors for each data point. When t-SNE constructs its high-dimensional probability distributions, it uses Gaussian kernels. Perplexity is directly related to the bandwidth of these kernels. A low perplexity value means t-SNE places a strong emphasis on very close neighbors, using a narrow Gaussian. This tends to preserve fine-grained local structures, potentially showing many small clusters. However, it can sometimes make the global arrangement of these clusters appear fractured or disconnected. Conversely, a higher perplexity value means a wider Gaussian, causing t-SNE to consider more neighbors further away. This encourages the preservation of broader, more global data structures, often leading to larger, more cohesive clusters. While this can provide a clearer overall picture, it might smooth over some important subtle local details. Choosing the right perplexity is like adjusting a microscope. Too low, and you see too much noise or tiny, meaningless details. Too high, and you blur out the distinctions you need to see. The recommended range for perplexity is generally between 5 and 50, but this is a guideline, not a strict rule. When you are actually working with your data, the best way to choose a perplexity value is to experiment. Try running t-SNE with a few different perplexity settings within that suggested range, perhaps 10, 20, and 30, and carefully observe the resulting embeddings. Look for a stable visualization where clusters are clearly separated but also reflected logical relationships. Consider the density of your dataset as well. Very sparse datasets might requiring a higher perplexity to find meaningful neighbors, while extremely dense datasets could tolerate a lower value. Remember, there is no single perfect perplexity for every dataset. It is an iterative process. Here is an insider tip. t-SNE also employs a clever trick called early exaggeration. During the initial optimization steps, t-SNE temporarily amplifies the attractive forces between points. This helps prevent points from getting stuck in poor local minima and encourages tighter, more distinct clusters to form in the final embedding. Understanding perplexity in conjunction with early exaggeration helps you gain even greater control over the visualization process. It is about understanding your data at multiple scales, from the very local to the global, much like adjusting a camera lens. Ultimately, your ability to intelligently adjust the perplexity parameter is key to extracting truly meaningful insights from your high-dimensional data. It empowers you to navigate the trade-off between local and global structure preservation, helping you uncover the hidden stories within your datasets. Mastering this parameter turns t-SNE from a black box algorithm into a powerful, tunable instrument for data discovery.